Hello friends, in first lecture I have talked about the system of linear equations in n variables and I explained how to express that system in matrix form and argumented matrix form. You are well familiar with solution of equation. For example, if I take just single equation, say x plus b or x is equal to b, a not equal to 0. So this is the equation in one variable x. A and b are constants. So for the solution of this, value of x which satisfies this equation is known as the solution. So x is equal to b by a. If I put value of x to be b by a, I am getting a into b by a equal to b. So b by a is solution of this. Now if I take say x plus by is equal to c. Now this is a linear equation in two variables x, y. A, b, c are constants. A or b not equal to 0. Then this is equation in two variables. And we know that geometrically this represent line, okay, whose x-intercept is by putting y 0, x-intercept is c by a. Suppose this is your c by a and this is some b by c by b. Then this line is your geometrical representation of x plus by equal to c. Every point on this line is solution of this equation. This is a line in plane. Every point means if I put x is equal to c by a and y 0, then this equation is satisfied. Or if I put 0 c by b, it is satisfied. If this point is some x1 y1 here, if I put that point here, that equation is satisfied. So that one equation in two variable has infinitely many solutions. But if I have some other line, if I take other equation, together with that a1x plus b1y is equal to c1. This is my other line, this is L1, this is L2. L1, L2. Then you will get some intersection point for this x1, y1. This intersection point is solution of these two equations. And you know how to solve these two equations. For this, what you have done, you have solved these two equations simultaneously. Means what you are doing, from second equation you are like expressing y in terms of x and you are putting that value in first equation. Then we will get that equation only in terms of x. We will get the value of x and again resubstituting that value in second equation, we will get value of y. So that is the way. Or what you are doing, you are multiplying first equation by b1 and second by b. Then we will get coefficient to be bb1 here bb1 and then this term get cancelled. In that way you are solving it. Then you have studied Cramer's rule method for this. So for Cramer's rule, what you have studied, x is given by dx upon d. What is dx? It is the determinant of matrix. What is d matrix? D matrix is matrix of coefficients of variables. So firstly, variable a, a1, b, b1. And in this d, if you replace column of x, this is the column of x. If I replace it by constant c, c1 and b, b1. Y is equal to dy by d. How to find dy now? So this is column of y coefficients. Okay, so to replace that column by constant C1 upon determinant D AB A1 B1. As these two lines are intersecting with this determinant AB1 minus A1B must not be 0. Must not be 0. Now, it may happen that for that two lines, this is first line and this is other line. And that two lines are parallel. These two lines are parallel. It may happen that these two lines are intersecting. Then that two equations have just one solution. That two lines are parallel to each other. So there is no solution for that two lines. And there is one more case. Your first line is say L1 here and second line is also L1. Is also L1. Means Ax plus By is equal to C. And if I multiply this by some constant 2Ax plus 2By is equal to 2C. So these two lines represent only one line. So in that case, if that both equations represent just single line, in that case, the two equations has infinitely many solutions. Infinitely many solutions. So you have studied solution of one equation, two equations in two unknowns. Also, you have solved three equations in three unknowns. Simultaneously, by using matrix inversion method, by using Cramer's rule method, we require all those concepts. Now, what is the matrix inversion method? What is the matrix form of this system? X plus By is equal to C and A1x plus B1y is equal to C1. The matrix form is AA1, BB1, this is your XY is equal to CC1 column vector. And if I denote this by X is equal to B, then X is equal to A inverse B. X is equal to A inverse B. So this gives us solution of the two equations. So this is matrix inversion method. Matrix inversion method. Now, for applying matrix inversion method, A inverse exists if and only if determinant A is non-zero. A must be non-singular matrix. And that is true for invertible matrix. Invertible matrix is a square matrix. And for that square matrix, you must have number of equations is equal to number of variables firstly. Here also D is in denominator. So Cramer's rule is applicable only when D is non-zero. Means corresponding matrix is invertible. Is it right? So there are limitations of matrix inversion method to solve the system of linear equations. So for applying Cramer's rule or your matrix inversion method, number of equations must be equal to number of variables. In addition that, your coefficient matrix A must be invertible matrix. Only in that case I can apply Cramer's rule and matrix inversion method. If I have 5 equations in 4 unknowns, 5 equations in 10 unknowns, then how to solve the system? Or just a single equation x plus by is equal to c. That equation has infinitely many solutions. In that case, it is impossible to apply matrix inversion method or Cramer's rule method. Or if I have system of number of equations in which number of equations is equal to number of unknowns, but coefficient matrix is not invertible, then your matrix inversion method or Cramer's rule method fails. It is not applicable. Then if I have a number of equations not equal to number of variables, so it is non-square system say, then how to solve that system. It has also solution. If I just take x plus by equal to c, it is a system of one equation in two unknowns and it has infinitely many solutions. In three-dimensional, if I take the two planes, then if that two planes are intersecting to each other, then geometrically we can observe that intersection of that two planes is nothing but a line, and every point on that line satisfies that two equations in three unknowns. Line contains infinitely many points. So if I have three equations now, a1x plus b1y plus c1z is equal to, say, d1. Okay. So this is a plane. If I have just a single equation, then every point on that plane satisfies that equation, where a, b or a1, b1, c1 not equal to 0. One of coefficient must be non-zero, then it will be plane in three dimension. If I take e2x plus b2y plus c2z is equal to d2, I have two planes now. If that two planes represent one and the same, means find that two represents one and the same plane if these coefficients are in proportion. A2, B2, C2 and D2 are same scalar multiple of A1, B1, C1 and D1. Then that two planes represent, that two equations represent one plane, and in that case it has infinitely many solutions. Now it may have that two planes are intersecting. If you observe two planes are intersect, then that passes through just single line. So intersection of two planes is a line, and every point on that line is solution of that. So if these two equations have a solution, then what is solution set? Solution set is nothing but intersection line of that two planes. There are infinitely many solutions. Now if I take third one, a3x plus b3y plus c3z is equal to d3. These three planes may have unique solution. If I have three planes and third one is cutting to them, then it just cut in one point. Just cut in one point. Is it clear? If two planes are one and same, then and the other one is parallel to them, then there are infinite many solutions for that. And if all are parallel to each other, all three planes are parallel to each other, then there is no solution. There is no solution for that. So these three equations may have unique solution if that three planes intersect each other in just single point. The three planes intersect in one line, then there are infinitely many solutions. And if all are parallel to each other, okay, then there no solution for that three equations. So three cases are there. Three cases are there for the solution set of these three planes. So I have explained this geometrically. Now our aim is to solve this system with help of matrix. So I'll put this system in matrix form. Okay. Argumentative matrix form: A1, B1, C1, A2, B2, C2, A3, B3, C3, D1, D2, D3. And I will denote this matrix by AB. This is known as argumentative matrix. Then to solve the system simultaneously, actually what we are doing, we are trying to obtain one here. If you don't apply, by using that non-zero entry here, you can make below entries to be 0. Below entry is 0. Then we'll try to obtain second entry to be 1 here. So by applying sequence of row operations, sequence of row operations. This is get transformed to say 1, some entry here, 0, 1, some entry 0, 0, 1. Okay, and here D1 dash, D2 dash, D3 dash. We get something. Then from this we write reduced system. Reduced system. We will not always get form to like this. If there may be 0 here, there may be 0 here. Is it clear? If it has unique solution, then we will get always this form. We will get always this form. Then for this form is known as row echelon form of A matrix, AB matrix. This matrix corresponds to row echelon form of this, and whole matrix corresponds to row echelon form of this. So what is the row echelon form now? What is the row echelon form? If I take a matrix in which if it has 0 rows, if I take say 4 by some 5 matrix, it has 0 row, then it must be at bottom. If it has non-zero row, then in first row, first entry must be 1, 2, minus 1, 6, 3 by 2. If I get like this. Then in second row, 0, 0, say 1, 0 and 5. 4 by 5, 0, 0, 0, 1, minus 7 by 6. Observe this matrix now. This matrix has 0 row which is at the bottom. In other non-zero rows, if you observe, first non-zero entry in row, it is 1. So this 1 is called as leading 1. Okay, leading 1. So in any non-zero row, first non-zero entry must be 1, and if I compare two non-zero rows, then leading 1 appearing in upper row must be at left position than leading 1 appearing in below row, downward row. And if that matrix has 0 rows, then they must appear at the bottom. So such type of matrix is known as row echelon form. Row echelon form. Okay. This matrix is known as row echelon form of the row echelon form. Now in addition that, if I have now row reduced echelon form, this is your row echelon form, row reduced echelon form. 1, 2, 0, then 0, 0, 0, 0, 1, 0, 0. Oh, here there will be 4, 0, 0, 0, 1. Okay, and it doesn't contain leading ones. So 3, 2, doesn't matter. 0, 0, 0, 3. Good. Now, if you observe this matrix, it has 0 row which occurs at bottom. In any non-zero row, first non-zero entry is 1. If I compare two rows, any two row, non-zero rows, leading 1 in upper row is at left position than leading 1 in below row. So this is row echelon form. And now observe that column containing leading 1. This is leading 1, this is leading 1, this is leading 1. In column containing leading 1, all remaining entries are zeros. This doesn't contain leading 1. This contain leading 1, so other entries are zeros. This contain leading 1, other entries are zeros. This doesn't contain leading 1. If there is leading 1, it must be here and then other entries must be 0. And that's why this form is known as row-reduced echelon form. Row-reduced echelon form. Now, if I take any matrix, m by n matrix, and if I apply the proper sequence of row operations, it is always possible to convert reduced matrix to its row echelon form or row reduced echelon form. In that row echelon form, number of non-zero rows is called as the rank of that row echelon form as well as its any equivalent matrix obtained by ring row operations applied on it. So if some A matrix is given and by applying suitable sequence, you will get next matrix say A1, then A2, A3 and this is your R. Then rank of this matrix same as rank of previous one, A3, A2, A. Rank of each of previous matrix is also 3. So what is the rank? Rank of matrix A is nothing but number of non-zero rows or number of non-zero rows in row echelon form or row reduced echelon form of that matrix. And that rank is precisely equal to number of leading ones of that matrix. This rank plays a very important role while solving the system of linear equations. With help of Gauss elimination and Gauss-Jordan elimination method. So Gauss elimination method depends on row echelon form of the matrix, while Gauss-Jordan elimination method depends on row reduced echelon form of the matrix. With help of row echelon form of matrix, if I write the reduced system, then I will get from last equation solution for last variable. Substituting that in up equation, I will get the next variable value. Substituting that in up equation, I will get next value and so on. So if I solve system by using Gauss elimination method means back substitution method. Okay. And with help of row reduced echelon form, I am getting in reduced system, say this is x is equal to 2, then you have the z is equal to, okay, y you have to find out, then z, right, this is the x, y, z, w, z, okay, and this is your row echelon form. So, number of leading variables gives us number of leading, once gives number of leading variables for that system and there is one non-leading variable which corresponds to column containing non-leading 1. So this column doesn't contain leading element. So variable corresponding to this is say y. So in that case, I will call that y as free variable. And due to that free variable, the corresponding system has infinitely many solutions. So from Gauss-Jordan elimination method, we get direct solution. So Gauss-Jordan elimination method is also known as direct method, while Gauss elimination method depends on back substitution and it is solved with help of row echelon form. Row echelon form. So this is a discussion about row echelon form, row reduced echelon form, rank of matrix, and how that row echelon forms will be helpful while solving the system. And on that row echelon form and row reduced echelon form, we have two methods, Gauss elimination method and Gauss-Jordan elimination method. We'll study those methods in next lecture. Thanks for listening lecture carefully. Bye bye.